Assalamualaikum. In our lab 4, we are required to do two tasks, which is task 4.1 is computing the DFT, and task number 2, 4.2 matrix representation of the DFT. In task 4.1, we are need to required to use the MATLAB software, which is for the task 1, we need to develop our own DFT function to help our understanding on how the DFT comes from the DFT. In MATLAB, I need to develop our own function, which is DFT EQN. We can use this coding to develop our own function. After we create our function, we also need to define the variables and define the equation. For task number 2, we need to test our routine DFT EQN, our function, for each cases, which is in cases A, Sn equal to delta n for n equal to 10. In MATLAB, we can define the n value and the Sn and call the function, which is the function that we are already developed, which is x dft1 equal to dft equal x. We also can plot the graph using this coding. After we plot this graph, we can get the graph as this graph, unit step graph. For the cases number B, Sn equal to 1 for n equal to 10, we can test our coding in MATLAB using this code. The coding is same with the first coding, but we need to change the value for the xn, which is in this line. Sn equal to 1 bracket 1 n. We also can use this coding to plot in the graph. This is the graph for the cases number B. The cases number C, which Sn equal to exponent j2 pi n divided by n for n equal to n. In our MATLAB, we are changing the Sn value while using the same code. We also can plot in the graph. After we plot in the graph, we will get the graph as this. For the cases D, Sn equal to cos 2 pi n divided by 10 for n equal to 10. In our MATLAB, we also use the same function, the same coding, while we change the value for the xn, which is s equal to cos 2 pi n divided by n, which is n equal to 10. We also call the function and plotting the graph. After we plotting the graph, we will get the graph as this unit step graph. So in the task number 3, we are required to write a second MATLAB function, which is for the inverse DFT. The function name is x equal to I DFT equal x for computing the inverse DFT, where x is the endpoint vector containing the DFT and x is the corresponding time domain signal. So in this task, in MATLAB, we use the same function to create our function, to develop our function. So this line is for we create our own function x equal to IDFT for inverse function x. We also need to define the variables and define the equation. Also required to do the same routine test for each cases. For cases A, we can test into our MATLAB by using this code. We need to define our n and xn cases 1 zeros 1 bracket 1 n minus 1. We also define our small n and call the function for the DFT equal x. And then we also need to inverse IDFT of the above signal, which is use this code. For plotting the graph, we need to plotting two graph, which is the original graph and the inverse graph by using these two code. After running our coding, we will get the graph as this graph, unit step graph, which is this is the magnitude for our signal. From the graph, we can observe our original and inverse have a same value, have a same graph. For cases B, we can run in our MATLAB coding as the same function, which is the cases A, but we need to change the Sn value for x equal to 1 bracket 1 n, and we also need to define our n minus big N and call the function for the DFT equal n for the cases B. And we also can find the inverse DFT of the above signal for cases B. And then we also can plotting the original and the inverse graph by using the same coding. After we run this coding, we will get the plotting graph as this graph. For the cases C, we can running the code in our MATLAB, also using the same function, but we just need to change the value for Sn, which is Sn is equal to ESP bracket 2j pi n divided by n. We also call the function for the DFT in cases C, and find the inverse DFT for the cases C, and plotting the same graph, the two graph for the original and the graph for the inverse. After we running these two code, we will get the plotting graph as this graph. So for the last cases for the D, as in our MATLAB coding, we use the same code, but you change the value for Sn according to the D cases, which as x equal to cos 2 pi n divided by n, which is n equal to 10. And we also use the calling function for the DFT eqn for the cases D, and find the inverse DFT for the above signal for cases D. We also using the same function for plotting the graph, original graph and inverse graph, which is after we run the coding, we will get the result as this graph. In the conclusion, we can conclude that the original and the inverse graph will get the same signal.
In part 4.2, the matrix is represented as a metric vector product. On question 1, the A equal to the DFT matrix that returns the n times n DFT matrix is generated by using the MATLAB function. To generate the DFT matrix, the function of A equal to DFT matrix is declared at the first beginning of the MATLAB coding. After that, the variables A is defined. The for loop is used to build the n times n DFT matrix. Finally, at the end of the operation, the n command is used to terminate the command. After conducting the simulation, the DFT output is displayed in the command window. The DFT output is displayed as a metric vector form. So, the DFT of the following signal is computed by using matrix A. At the beginning, the value of n is set equal to 10. After that, the Twiddle factor W equal to exponential negative 2i times pi over n is defined. The matrix of A is initialized equal to A equal to zeros and n. On the next line, the DFT matrix is defined to order the construct of matrix of A. For question A, the equation of the xn is defined as x equal to 1, 0s, 1, 9. Then the xn equation is multiplied with the matrix A to compute the DFT of xn. After that, the magnitude of DFT is plotted by using the figure command, while the stem command plots the discrete magnitude. After the simulation is run, the output of DFT is 1 times 10 matrix with all of the value equal to 1. Furthermore, when k is greater than 10, the amplitude of magnitude plot for the x equal to 1. So this is the result for the equation A. The vector form and the signal. So next, for question B, the equation of xn is defined as x2 equal to 1, 1, 0 on line. Then the DFT of equation xn is computed by multiplying x2 with matrix A. The output of DFT of x2 is displayed in the command window after running the simulation. From the output, only column 1 through 4 have a value 10 at k0, whereas the others have the value equal to 0. Aside from that, on the magnitude plot, the amplitude of the FT unity is equal to 1 at k equal to 0, whereas other are equal to 0. So this is the unity graph. For equation C, the off value n is from 0 to 9 is defined by using n equal to 0, 9. After that, the x3 equal to exponential 2i times pi I times n over n is defined as xn. After that, by multiplying x3 with matrix A, the DFT equation xn is obtained. After running the simulation, the output DFT of x3 is shown at the command window. The magnitude in columns 1 through 4 of the output is equal to 10, whereas the magnitude in the rest of the output is equal to 0. On the magnitude plot, the amplitude is plotted as 10, where k equal to 1 while it is 0 otherwise. So this is the graph for the question C. So for the third question 3, the inverse express the matrix vector products in question 3. The analytic expression of the inverse DFT matrix B is, then the function B equal to IDFT matrix that returns the n times n inverse DFT matrix is generated by using the MATLAB function. To begin with, the function command is used to define the B equal to IDFT matrix is generated by using the MATLAB function. The value of n is initialized to 5. For the loop is used to generate the matrix x n times n IDFT matrix of B. After running the simulation, the output of inverse DFT is shown in the command window. After running the simulation, the inverse DFT matrix is displayed in matrix vector form. So after running the IDFT matrix, we get the solution here at the command window. Next, for the question C, that compute the matrix A and B for n equal to 5. Then compute the matrix product C equal to BA. So this is the coding that have been computed. Then after we run it, we get the DFT matrix for n equal to 5 is A, n equal to 5 is B, and the product of C equal to BA for this vector form. And lastly, for the question 4 is to compare my answer of DFT equation and DFT matrix with the built in MATLAB function FFT. So after we define the n, we define the xn, which is x1, x2, x3 and x4, and use FFT to compute the DFT of the signal Sn, x1, x2, x3 and x4. Then plot the magnitudes of the DFT and combine the MATLAB coding, and after we run it, we can get the result at the command window. That's all from me. Thank you.